Hello, are we live? Yeah, we're live. Okay, let's go. Okay. So guys, I'll be I'll be I'll be preparing for TensorFlow certification exam. So for this one, I'll be going through this all these tutorials and covering everything here, and also and also starting from the basics, tutorials, beginners, experts level, everything. We're going to cover everything. Okay, load entry process, and also we'll go through each of the each of these most of this library, like for example TensorFlow, and then for production users we'll be using TensorFlow extended. So if you don't know about if you don't know about TensorFlow extended is, as it says, it's an end-to-end platform for deploying production ML pipelines, right? So it's very comprehensive, and it's very useful for deploying your machine learning application. Okay, so with that being said, let's get started. One thing to notice is that um, we'll be using Google Colab for coding it, and what I'll be doing is, let's just go for the quick start for beginners, just to see how to perform this task. Okay, so what I'll be doing is, I'll be using Google Colab. Okay, Google Colab to code this. Okay, and as we go, I'll be explaining everything, each and every point, how does something works, how it works basically. Okay, so let's just go. What name should I give it? Okay, let's get rid of it, and let's just we'll see it later. Okay, and then let's just TensorFlow to quick start for beginners. Okay, save the name a bit. What? Okay. Okay. Okay, we're there. Okay. So what I'll be doing is, let's just first do it this way. Okay. So guys, I'm also learning as I go. So I'll be I'll be I'll be seeing the tutorial, understanding what's going on underneath the hood, right, and then coding it in the Google Colab. Okay, so okay, so let's see what they're saying. Okay, so this short introduction uses Keras to build a neural network that classifies images. Okay, train this neural network, and then finally evaluate the accuracy of the model. Okay, so it's a classification model. Okay, and then yeah, it's just some configuration for Google Colab, which we have already done it. Okay, so let's just go ahead and import TensorFlow. as in the tutorial. Okay, and then we'll load and prepare the MNIST data set, and then convert the sample images from integers to floating point numbers. Okay, so let's just first load the data. Datasets.mnist. Okay, and then xtrain ytrain xtest ytest equals to mnist.load data. Okay, so mnist.load data basically returns this 4 tuple, okay, which is xtrain ytrain xtest ytrain and ytest, and this have training data and testing data, which is the original MNIST data consists of like original data set consists of 70,000 images, I think. Then 60,000 images is for train. You see, 60,000 images for train, 10,000 images for test. Okay, so yeah, that it will be doing that, right? As you can see here, xtrain.shape, ytrain.shape, xtest.shape and ytest.shape. Okay, alright, see here. Okay, and then let's just convert it into from integers to floating point number. Let's see what first what does it contain. Okay, it's 60,028, right? So let's just grab the first element. Okay, first matrix. See here, it's a number between 0 to 255, right? Which is generally a pixel value, and it's like it's a grayscale value. Okay, so let's just convert it into floating point integers. Okay, for the model's training stability, right? And then let's just build the model. Okay, and then here what they're saying is build the tf.ks.sequential model by stacking layers, choose an optimizer and loss function for training. Okay, so let's just build. Okay, let's just first see what the sequential API does for us. Okay, tf.ks.sequential. So sequential groups a linear stack of layers into a tf.ks.model inherits from model layer module. Okay, so what they're saying is it just groups a linear stack of layers into a tf.ks.model. So basically what it does is in deep learning what we have is this, right? We have hidden, we have a dense layer, right? This is a deep neural networks, right? This is input, and this blue nodes are this yellow node is input, blue node is hidden layer, and orange node is output layer, right? So each vertical layer is each vertical node or layer is in itself a layer which we can stack into sequential model, and it will build it sequentially, right? See this one, feed forward neural networks. Okay, so yeah, we can also see the example here. We instantiate the sequential API, and then we can also use the add API call and add this dense layer which contains 8 nodes into it, and this input shape is 16. Okay, and we can add as many layers as possible, right? We can build complex model as well. And here you can see arguments, right? Layers names, and then attributes, this matrix name running early, I mean, uh, there it is function for optimized by best performance and execution, right? So here we can add it, right? And then yeah, these are the um, arguments. Okay, yeah. Okay, so guys, I would highly recommend that you guys go ahead and just skim through it and see how it works. Okay, so let's just go ahead and add write this code. Okay, tf.ts.models.sequential, right? Do this, and then add a flatten layer, tf.ts.layers.flatten. See what does flatten do. Okay, this what does flatten layers do is it flattens the input, does not affect the batch size. Okay, so note, if inputs are shaped batch without a feature axis, then flattening adds an extra channel dimension and output shape is batch 1. Okay. Okay. Okay, what do you think? If inputs are shaped with batch without a feature axis, then flattening adds an extra channel dimension and output shape is batch 1. Okay, so it's just saying that if input doesn't contain a feature axis, then it will add, it will expand the dimension. Okay. So let's just give input shape to it, 28 cross 28, because as we see this, it has this shape 28 cross 28, right? So we'll do that. Okay, and then what we're going to do is we'll add a dense layer with 128 node, and then activation will be value function, right? And then we'll add a dropout layer with 0.2 probability of dropping out the connection, and then here.ts. will add 10, because this will be our output layer, and we want to classify number from, as we want to classify numbers from 0 to 9, right? 0 to 9, which is 10 in total. Okay. So yeah, we'll be talking more about activation function later. So there are many activation function. You can see TF activation function here. TF activation functions. Okay. So yeah, here you can use any activation layer. We are using value. And if we go there, right? So it says that applies the rectified linear unit activation function. So what it does basically is we have bunch of values, right? Then if we apply a value function to it, it will just what it does is it only accepts the value within certain threshold, right? So here's the function of value, right? So if the value is negative, then it will just flatten out, like y will be 0, output will be 0, and if it's x or it's positive value, the output will be as it is. Okay, so in this case, as you can see, all the negative values are dropped, right? Even z0 is 0, right? And then we only get we only get output of positive value as it is. Okay, and here you can also explore some other example as well. Okay, you can also click our value and write, and then we can also tune alpha as well. Okay, right? So which basically divides, um, I mean divides, I mean it takes the um, this kind of stuff, right? Okay, let me search it. Yeah, see this one, right? If the alpha value is 0.5, yeah, see the blue line, right? So it basically, I would say, it divides, I mean it multiplies uh, values with 0.5 if it's negative, but if it's positive, then it just take value, right, as same as the input value, right? That's it. Okay, so yeah, okay, um, all right, okay, so let's just um, define our model, and then what they're saying is, for each example the model returns a vector of logits or log odds, scores 1 for each class. Okay, so this logits and log odds is just, I mean if we don't define softmax from this acquisition function, by default it takes softmax. Okay, by default it takes softmax, and we can see what logits and log odds means. Okay, okay, so log loss, the loss function used in binary logistic regression. Okay, log odds, what does it mean is the logarithm of the odds of some event. Okay, so we have some probability, right, and then we take the odds p by 1 minus p, occurring, not occurring, and then we take the log of 9, right? So these are the log odds. Okay, 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 um, okay, so let's just okay, let's just follow these steps. We'll do model, we'll pass uh, value this, right, up to 1. We'll pass only one input, 28 cross 28, and then we'll take the numpy of it and see what does it return. Okay. So basically, without even training the model, we just pass the input value, and these are the logits that it returns, right? And these logits, what does it represent is the probability that, or expectation value, I should say probability that whether the value is from 0 to 1. So in this case, wait, okay, I think okay, yeah, so it's just a prediction, I mean it's just a raw prediction. So yeah, we'll see later what does it mean, right? Okay, so then what we are doing is the tf.nn.softmax function converts these logits to probabilities for each class. Okay, yeah, we haven't passed softmax, we haven't passed predictions to softmax yet. Okay, so let's just pass it. Okay, okay, yeah, so now it's converted to probability, and if we just skim through it, we see that it's predicting the number to be, this 0. Okay, so let's read the note, what it's saying. Now it is possible to bake this tf.nn.softmax in an activation in as the activation function for the last layer of the network. While this can make the model output more directly interpretable, this approach is discouraged as it's impossible to provide an exact and numerically stable loss calculation for all models when using the softmax output. Okay. Oh yeah, guys. So they are just saying, they are just putting a note that putting a note for numerical stability while using tf.nn.softmax. So I would recommend that you guys look the documentation for it. Let's just go ahead and see what it's saying basically. Okay. Used for multi-class predictions, the sum of all outputs generated by softmax is 1, which is, yeah, it's because it's probability, right? So this function performs the equivalent of this. Okay. So tf.exponential of logits, take the exponential of that, and then tf.reduce sum tf.exponential of logits from axis. Okay. So what does this reduce sum does? Alright. Okay. Computes the sum of elements across dimensions of a tensor. Okay. So if we take tf constant this 2 cross 3, and then x dot numpy is 2 cross 3. So the sum of all elements will be 6. Okay. So this is what reduced sum does. Okay. Okay. And if we specify dimension 0, then just 1 1 1 and then plus 1 1 1 just 2. Okay. Take dimension to be 0, then it just returns this. Okay. 2. Then if we take 1, which is this 1 column, 0 means row, sum column, and then sum across the column. Okay. 3 and reduce sum 1, keep dimension true, numpy. So what we'll be doing is this array 3 3. Okay, then reduce along both dimensions. The result is this. Okay, so by default it reduces along both dimensions. So that's why it's just sum all it up and then it's 6. Okay, it's just the output is just the sum of all both dimensions. Okay, you see here 0 and 1 numpy. Okay. Yeah, so let's just go ahead and read. The losses dot sparse categorical cross entropy loss takes a vector of logits. Okay, takes a vector of logits at this value. Okay, and then and a true index and returns a scalar loss for each example. Okay, it's scalar loss. Okay. This loss is equal to the negative log probability of the true class. It is 0 if the model is sure of the correct class. Okay. This untrained model gives probabilities close to random 1 over 10 for each class. So the initial loss should be close to minus tf.max.log of 1 over 10, which is this. Okay. Okay, so it's just the probability would be just 1 over 10. The probability of occurring, probability that any of the input is number between 0 to 1 is 1 over 10, cause everyone is equally likely, every number is equally likely to happen. So the sample space is 10, and our occurring of uh, sample space is 10, and occurring of the event is 1, so 1 over 10 will be the probability, and the negative of that will be our loss, this loss, right, this loss function. Okay, alright, so let's just code ahead. Loss function equals TF dot losses dot sparse categorical cross entropy, and then we'll set from logic to true, and do we have, yeah, okay, alright, so let's just calculate the loss function for one of the label in this predictions on dot nullify. Okay, see this one. Okay, so what, how it's doing is this loss is equal to the negative log probability of the true class, if it is 0 if the model is sure of the correct class. Okay, yeah, so if our prediction turns out to be the level of y, this, which is 5, right, if it will be, it will be 0, right, this value, this function will return 0, but right now we are just getting this, right, 0 label, which is not true. That's where the loss is 2.85, right? So yeah, yeah. 0 and 5. Yeah, I think we'll see ahead, more examples of it. So yeah, like actually we can just go ahead and see right now. Okay, how does it work? Okay, so we have y true this, y prediction this. Okay, so using auto sum over best size prediction type, then this, sparse categorical cross entropy, this. Okay, let's just go ahead and look stack workflow. Alright, let's see how does it calculate. Okay, sparse categorical and cross entropy both compute categorical cross entropy. The only difference is in how targets or labels should be encoded. When using sparse categorical cross entropy, the targets are sent by the index of the category starting from 0. Your output is okay. I think we can just look at the formula. Okay, so the log probability of true class. Okay, log probability of true class. So probability that it's 5. What's the probability it's 5? The prediction will be 5, right? Okay, so I'm guessing, yeah, prediction on this 0, 1, 2, 3, 4, 5. Okay. Um, 0, 1, 2, 3, 4, 5. This is the probability of it. And then if we go ahead, tf dot, let's take negative of it, tf dot math dot log, paste into it, and then what we'll get is, see, voila, this is the value we get. Okay, so this is what it's showing. Okay, this 2.85, right? Rounding to I mean, it's not rounding, yeah, it's just showing this value. Okay, yeah, so this is how it's calculating, okay, the loss. So we'll just go ahead and compile the model. Okay, optimizer Adam, and then we're taking loss as loss function, and then matrix as accuracy, because we are solving a classification problem. Okay, so guys, going forward, will be, going ahead, in the future we'll be talking more about what is optimizer function, and we have seen the loss function right now, right, today, and then we'll be going more depth into loss function as well. Okay, and we'll also see some metrics, what metrics we can monitor for our model. Okay, let's just compile our model, and also we can also see the architecture of our model. Okay, so it takes takes input as this, okay, flatten, and then we passed into 128 layer of dense layer, then we have dropout, and then right, and then we have output layer. Guys, we'll be talking more about these parameters, right? See, in the dropout layer there's no parameter, because it's just the model doesn't have back propagation, which we'll be talking later, right? Back propagation algorithm, which is this optimizer, right? So that's how the parameters are being calculated here. Okay, so let's just go ahead and see the next steps. Okay, the model.fit method adjusts the model parameters to minimize the loss. Okay, so if they are saying is that model.fit method adjusts the model parameters to minimize the loss. So what it's saying is, we have optimizer as Adam, right? We have loss function, so it will just iterate through every example and optimize the loss function, and and increase our accuracy. Okay, so let's just see what does this do from the documentation. Okay, trains the model for a fixed number of box iterations on a data set. Okay, yeah, all right, I think it was clear. I mean, it's just adjust the method to adjust the model parameters. Model.fit is just adjust the model parameters to minimize the loss, right? Just minimize the loss, and in result increase the accuracy. Okay, so we'll just call model.fit with passing our data x train, y train, epochs to 5, and let's just train it. Okay, five epochs. All right. Okay, so our model is trained. So let's see the next step. The model.evaluate method checks the model performance usually on validation set or test set. Okay, let's just evaluate our trained result. Okay, so yeah, see, the accuracy of our model is 97%, right? Loss is 0.07, right? And yeah, I think yeah, it performed very well. Okay, so let's read the next step. The image classifier is now trained to 98%. Yeah, true. Okay, around 98% accuracy on this data set. To learn more, read the TensorFlow tutorials. Yeah, okay, if you want your model to return a probability, you can wrap the trained model and attach the softmax to it. Okay, probability model will be the rest of sequential. You can wrap it layers.softmax. If you want your model to return a probability, you can wrap the trained model and attach the softmax to it. Okay, yep, you can do that. Probability model x test 5 or 3. Okay, you can do 5 as well. 3 plus 10. Okay, so this is the probability of each test result. Okay, so if we see like 0, okay, and then so what is it? Y test 0. Y test 0 is it's 7. Okay, we can do we can take this, right, dot numpy dot 0, and then we can do argmax into it. Right. See, our prediction and the test results match. So yeah, the model predicted it very good. Okay, so yeah guys, so that was it, and I'll see you in the next video. Thank you. So yeah, this was helpful. Thank you guys, see you later. Bye for now. Yeah.